Today, on how it's made. Seatbelts. This story will keep you glued to your seat. Windows. No pain, no gain. Wax figurines. A centuries-old cloistered craft revealed. And hot air balloons. Around the factory in 4.5 minutes. It's an indisputable fact that seatbelts save lives. When a car comes to a sudden stop, the seatbelt prevents you from hurling forward. It spreads the stopping force across the sturdier parts of your body, namely your rib cage and pelvis. This spreading action dilutes the strength of the stopping force, minimizing injury. Before production can begin, the factory has to adjust the seatbelt design to fit the specific car model, to make sure the belt path is clear, that there's enough room for rotating parts to move, and so on. On the factory floor, robots assemble most of the mechanical components. This plastic disc, containing a spring and a weight, is part of the locking mechanism. It's what stops the seatbelt straps, called the webbing, from lengthening when you jerk forward due to a sudden stop or hard deceleration. The locking mechanism goes into the seatbelt's retractor mechanism, the component that lets the webbing extend and retract. The webbing will wind onto this aluminum spool in the retractor, a rewind spring keeping it taut. Sudden deceleration will cause this silver ball to trigger the locking mechanism. This will stop the spool from rotating and lock the webbing. This next robot assembles what's called the pretensioner mechanism. While the locking mechanism stops the webbing from lengthening, the pretensioner sharply pulls the webbing back, tightening any slack. The pretensioner kicks in only in the event of a crash. The sudden deceleration on impact triggers sensors which signal the airbag control module to send an electrical charge to the pretensioner. This charge sets off a tiny explosion that deslacks the belt. This worker installs the explosive device called the microgas generator, or MGG. After lubricating the inside of its aluminum cylinder with grease, she inserts a piston and the MGG. The MGG contains a chemical called nitrocellulose. The electrical charge coming from the airbag control module ignites this chemical, causing a tiny gas explosion. That generates pressure within the cylinder, driving the piston upward at high speed. This triggers a gear that winds the retractor spool backward, taking up any slack in the webbing. After capping off the microgas generator's housing, a robot transfers the completed pretensioner mechanism to the retractor's frame. Then it screws on a steel cover plate to hold the pretensioner in place. They install the rewind spring onto the spool of the retractor mechanism. This spring is what provides resistance when you pull out the webbing to buckle up. Then when you unbuckle, it rotates the spool to rewind the webbing. The car company decides what type of spring to use. The thicker the spring and the more coils, the greater the tension, and therefore the faster and smoother the belt retracts. But the greater the tension, the less comfortable the seatbelt is on the body. The webbing is made of woven polyester fiber. This machine sews one end over into a loop for the pin that'll anchor the webbing to the spool. The pin is made of either plastic or steel, depending on the type of retractor they're using. A worker now threads the end through a machine that automatically winds the webbing onto the retractor spool, making sure the pin is properly attached. At the same time, the machine checks the overall belt length to make sure it conforms to the client's specifications. At this factory, every single seatbelt component has to pass a thorough quality control check. Here, a machine checks a key safety feature, a lever and ratchet mechanism that prevents the webbing from extending after you've belted in a child car seat. Now for the final assembly. Workers load all the seatbelt parts in a jig, a holding device that arranges them in the proper configuration. A worker feeds the webbing through the shoulder loop, from which the belt hangs, and through the tongue plate, the part that clicks into the buckle. Both these components are made of steel for strength, with plastic coverings matching the car interior. The last step is to sew the anchor to finish off the other end of the webbing. Every seatbelt design goes through extensive testing before going into production. This machine assesses how much pull the webbing and retractor can withstand before breaking. This machine tests the webbing's durability, running it through 50,000 abrasion cycles to ensure the material doesn't wear out. The earliest windows were merely holes cut into walls. People living in warm climates left them uncovered, while people in harsher climates used animal skins to keep the cold out. In the Far East, people covered the opening with paper. Then came glass panes, in sashes that swung in or out or hung one above the other. This type of window is called a casement window. A crank mechanism opens it at an angle. To build the window frame, the factory begins with 5-meter lengths of extruded PVC, a type of plastic. As clamps hold the PVC steady, a computer-guided circular saw cuts the sizes required for the frame. The same machine also cuts the pieces for the sash, the inner frame around the glass. Each frame is made from 4 pieces, whose ends are mitered at a 45-degree angle. Now workers load 8 pieces onto a computer-guided welding machine. 8 because it welds 2 frames at a time. First, a heating block, whose temperature is 230 degrees Celsius, melts the ends. Then the machine pushes them together. They fuse, forming the frame's 4 corners. Here's the same process viewed from above. As the melted ends bond under pressure, excess PVC oozes out at the joints, then hardens. The next machine will clean that up. A robot reads the profile of the specific frame style. Then it uses one of several cutting heads to shave the excess off the corners. From here, the sash and frame go to another area to receive hinges. Meanwhile, workers cut the glass to size. They start with a huge sheet measuring about 2 by 3 meters. It's very heavy, more than 90 kilograms. So they lay it on a specially designed table. A blower sends up air through tiny holes. This floats the glass just above the surface, making it easy to move around. They score the glass using a sharp carbide cutting wheel. This window will have what's called a thermopane, 2 panes of glass with argon gas in between for insulation. One of the panes has a transparent metallic coating to reflect the heat back into the house. They adhere a strip of silicone foam around the perimeter of the first pane, notching it for a good fit around the corners. The foam is covered in a thin, strong polyester film to prevent the gas from leaking through. The strip is a spacer, creating a 1.5 centimeter gap between the 2 panes. That's where the gas will go. They cut a hole at the top of the spacer and another at the bottom. You'll see why shortly. This window features decorative grid work called muntin bars. They're made of aluminum and go between the 2 panes. A worker lays the bars onto the first pane, then uses this guide to line them up perfectly straight. Then she puts the second pane on top. It sticks to the exposed adhesive edge of the spacer. Now the double pane glass goes through a press, whose rollers apply pressure to ensure a strong and thorough bond to the spacer. After the glass exits the press, workers pump in argon gas through that hole at the bottom of the spacer. The speed of the gas flow is critical. If they pump it in too fast, it'll mix with the air in between the panes, rather than push it through the hole at the top of the spacer. After plugging the holes, they coat the spacer in a polyurethane sealant. This makes the thermopane completely airtight. Now it's ready to go in the sash. A piece of PVC called the glazing stop holds it there. They snap it in place using a roller. A little PVC cement to seal off any minuscule gaps in the corners. Then the sash goes into the window frame. Their respective hinge parts simply snap together. The last step is to snap the frame's crank arm onto the sash. Making religious figurines out of wax is a tradition the French brought to the New World. For hundreds of years, this delicate craft wasn't open to any Tom, Dick, or Pierre. The technique remained a closely guarded secret, practiced only by monks and nuns within the confines of their monasteries and convents. Well, now, the secret's out. This artisan uses a centuries-old technique to restore antique figurines and to make new ones. She begins with pure beeswax, paraffin wax, some powdered chalk to make the waxes less transparent, and a bit of solid animal fat to make the wax less fragile once it hardens. She heats the can of ingredients in a pot of water for about 2 hours until everything's melted and homogeneous. Then she tints the mixture using oil paint pigments. There's no exact recipe. She goes by gut feeling, fiddling with various colors until she creates the exact skin tone she's looking for. Once she's certain the color is uniform throughout, she pours the mixture through a stocking. This filters out any contaminants or undissolved particles. Now she pours the mixture into a plaster mold. There's a different mold for each figurine model. This one's a baby Jesus. The wax takes about 10 minutes to solidify. The figurine comes out easily because she's greased the mold cavity beforehand with filtered sheep fat. The figurine at this point is firm enough to extract from the mold, but still soft enough to sculpt. With a very fine blade that she heats over a flame, the artisan now scrapes away the seam left by excess wax that oozed out of the gap between the mold's two halves. Then she runs the figurine through the flame, just long enough to melt off any wax particles left behind by the scraping. After smoothing the surface with a solvent, she signs the back of the figurine with her initials. Then uses the flame once again to melt off the scraped out wax. Now that the figurine's body is finished, she can begin the detail work. She melts pine resin with beeswax to make glue, then brushes it onto the figurine's head. Then she takes strands of human hair. Clients often supply their children's, and soaks them in water. She wets strips of fabric as well. Then she rolls the hair around a knitting needle to make curly locks. She winds the fabric over the curls to hold them in place until they air dry. If she's pressed for time, she'll dry them in the oven on low heat. To make bigger curls for a larger figurine, she simply uses a thicker knitting needle. Now, using a hot blade to reheat and activate the glue, she applies each length of curls individually. Once she's finished covering the head, she attaches a little halo made of brass wire, heating the end so that the wax melts on contact and holds it in position. Now, using a small pointed tool that she repeatedly heats on the flame, she sculpts the fine facial details: the figurine's eyes, eyelids, nostrils, and lips. Again, a little solvent cleans off the wax particles. Now she brushes the figurine head to toe with powder made of pumice and pigment. This will help the watercolor paints adhere to the wax. She paints the eyes, lashes, brows, and lips. Once the paint dries, she applies a touch of varnish to the eyes to make them shiny and bright. Once the varnish dries, she dresses the figurine and positions it in its setting. The first passengers ever to ride in a hot air balloon were a sheep, a duck, and a chicken. That 8-minute flight took place in France in 1783. Today's hot air balloons work on the same principle. The burner heats the air, the balloon envelope holds the air, and the basket carries the passengers. Only today's passengers tend to be humans. Hot air balloons fall under government aircraft regulations, so their engineering has to meet very specific performance and safety standards. Once the technical design gets approval, the factory works on the graphic design. The computer renders the graphics into plans that resemble a giant jigsaw puzzle. Each piece has a code number. The computer generates a paper template for each one. Balloons usually fly in the early morning when there's still dew on the ground, so the nylon fabric with which they make the balloon envelope has a silicone coating to repel moisture that would generate mold and mildew. After tracing each template with grease pencils, they cut the fabric by hand and mark the corresponding code number on the back of each piece. Then, following the plan, seamstresses sew the pieces together like a giant quilt using heavy-duty thread. The type of seam they stitch is the strongest possible, what you typically see on jeans. They sew the seams to nylon straps called webbing. These run both horizontally and vertically, forming a giant grid. Should the fabric rip, the seam and webbing combined prevent the tear from spreading. Hot air balloons often carry a corporate logo. Workers divide the design into components, project each one onto a piece of fabric, trace it, and cut it out. They first glue, then sew the components to the balloon in one of two ways, either into the fabric or on top of it, as we see here. Stainless steel aircraft cable connects the balloon envelope to the basket below. Workers slip a plastic sleeve, then a copper sleeve over one end, then loop the cable. They line the loop with a stainless steel thimble. This thimble will protect the aircraft cable from damage due to wear and tear. They crimp the copper sleeve to lock the loop. After taking various measurements to ensure everything conforms to strict specifications, they wrap tape around the sharp end of the crimp. Then, using an industrial heat gun, shrink wrap the plastic sleeve over it to seal the connection. The basket is made of wicker or a similar natural material woven over a stainless steel frame. Wicker is flexible enough to absorb the shock of a bumpy landing. They cover the bottom edges with rawhide to protect the wicker when it scrapes against the ground. They pad, then cover the top edge in suede or leather for comfort when you're leaning on it to admire the view. These nylon poles, called uprights, fit into the frame. They support the burners above the basket. Hot air balloons run on propane, the same stuff gas barbecues use. Only a barbecue produces about 70,000 BTUs of heat, while a hot air balloon's two burners together generate 30 million BTUs, enough to warm a large building. After connecting the basket to the burner frame with cables, they cover the cables and uprights in protective padding. Then they hook up the hoses running from the burners to the propane tanks housed in the basket. Now for the final assembly. First, they tip the basket onto its side. Then they take those looped cables they made earlier and hook one end to the frame of the burner system. The other end is already hooked up to the balloon envelope, one cable to every vertical strip of webbing. Depending on its size, a balloon has between 12 and 28 of them. They form the skeleton of the balloon, carrying the weight of the craft and its passengers. After laying out the balloon envelope, they use a fan to inflate it partway with cold air. This takes 5 to 20 minutes, depending on the size of the balloon. Then they fire up the burners to heat the cold air. It expands to fill the envelope. The fabric near the burners is fire resistant. Because hot air weighs less than cold air, it rises, pulling the balloon upright and off the ground. You control vertical movement by manipulating the envelope air temperature. To ascend, you turn the burner flames higher. To descend, you pull a cord to vent hot air at the top. You can't... The trick is to ride different wind currents. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at www.howitismade.net.